Yeah, it seems like there is the. Do you know how to hide these two, or they stay here? Maybe.
Yeah. Not sure. It would kind of. No, this is.
Yeah, it's like Zoom, so I think it's like yeah.
For this, I don't know.
Well,
that's okay.
We can survive with this. Yeah. But this one is.
That goes away.
Okay.
Yeah.
No worries.
No, so you are sharing screen, and that's just.
That's for us. Yeah, we only have to see that.
Okay, so I have a couple of slides just to give you the context of what I'm showing later, because we have a couple of systems, so you have to know where I'm running commands, and then I have a toy code for today. It's 3 loops basically, not a big deal, but I mean then we can start thinking. So we are basically showing methods that we are applying also to the Plasma codes. Okay, so what I'm showing the toy code just because we are in a public event and so on. So that's the reason why. So first of all, the environment. As we said, as Marco explained yesterday, we have a small lab in which we have RISC-V system all connected to the same network. So you first SSH to a gateway, and from there you have Slurm that allow you to either access commercial Scala RISC-V platform. These are the one that Leon mentioned yesterday, the one that you can buy. Specifically, these are not in the market anymore, but anyhow, you can buy these kind of things. Here you have no vectors. Okay, so this is a standard Scala CPU. We have 7 of them. One is dedicated for compiling and testing, like a typical cluster, right? You have one node to do your test and 7 nodes to launch your jobs. Okay, and then we have 4 systems that are vector in compute nodes to run jobs with Slurm, same Slurm. So whenever you have your binary, your job script, you can either send it to this queue or this other queue. Okay, so I jump now to the chat just for you to. So this is my laptop. I jump to the login node of our lab and start here at USSH RISC-V, and I end up on a Sci-5 board with 4 cores that corresponds to one of these. Okay, so starting from now, I am basically able to use the RISC-V software stack. I can load modules. The typical command that I do is loading our compiler, the LLVM EPI compiler. This is the emulator, the one that Matt explained yesterday, that allows us to emulate vector instruction on a Scala machine. We will see later and more details. And this is our instrumentation library, because today we are going to see also some graphical representation of our executions. Okay, so let me go back now to so this is the environment. Questions? And last slide of this presentation has a QR code that you can scan, and a form will open, and you can ask for an account. Whenever you ask for an account, you will be able to do exactly what I'm doing here. Okay, so it's not showing off. It's just that I'm showing on a toy code what you could do at the end of this tutorial. Okay. Call it tutorial or call it whatever. I mean, just okay. So
can I
yes.
ask, say, C5, how can we compare with the Raspberry Pi regarding the performance,
Yes, yes. From a practical point of view, I see two big differences. The first one is here you have an M.2 connector for your storage, while in the Raspberry Pi you always pass through the micro SD, as far as I know. Right? So this basically this has a PCI Express link. So you can plug a network card, you can plug an SSD. So in this sense, this is a little bit more complete board compared to the Raspberry Pi. Now I'm talking about the connectivity. About the performance, the core performance, I don't really have a benchmark to tell you is twice slower or twice faster. I would say that it's comparable. It's just out of my.
Well, I was comparing with the Raspberry Pi 3 and with these ones, it was more the same.
Okay, I mean, so thank you. Okay, okay, that's good. Yeah. Yeah. Anything else? Does anybody have a board like this? Do you already have experience running on this? You probably.
We're close so that we can get it.
Yeah, yeah. Okay, so let me go back to one thing that Marta presented yesterday. It is very important for knowing what we are doing today. So we have the three steps, the three levels that Marta was showing yesterday, right? So the first and the second level are access free. When I mean access free means that whenever you have the account, you can do this kind of things. And with this one is restricted in the sense that I'm going to show you what we are able to do here, but you would not be able to do it because you need access to a platform that is still not, say, publicly available. Okay? So it could be that it will become available, but right now they do not be. Okay. So and it's also this color code also correspond to an increasing level of complexity, call it complexity. We are working on 3 loops, so probably you can. Okay. So the first, as Marta was explaining yesterday, we are going to jump on here and compile our code and see if, for example, compatibility with our toolchain, with the toolchain that we have. I showed you that, for example, we are using a compiler, an LLVM-based compiler. Who knows if your code is compatible with that, and this kind of things. Okay? Here is also where we can start playing with the auto-vectorization. So we can tell the compiler, try to auto-vectorize and see what's going on. So we moved to here. Whenever you have a binary with vector instruction running on a scalar node, you will have illegal instructions. So we will use this VHAE emulator to emulate our vector instruction. Last step is jump to the FPGA that we have, that is this platform here, in which we have some I/O interfaces and the RISC-V core plus the VPU implemented in the FPGA. Here, this is really a compute node in which you have one core with the VPU. That was the red part that was in the slides of Marta. Questions about what we have, the 2 platforms we have. We have 2 platforms, and in one we can do 2 work, scalar or scalar plus vector emulation. The other one is the FPGA. Yes, please.
Would it be possible to do also some cross compilation from another node and just upload the binary?
Yes. It's actually possible, and it's also nice because this network file system is connected to the same network. So whenever you will have an account and you put a file here in your home, is visible here and here. And the binary that you generate here, you can generate it as you say. Sorry. Yes. No, it's fine. You can generate the binary here natively, so using a native compilation, or you can cross compile. Yes, that's
I think for compilation it might be a bit weak. There's no.
totally right. So you can be, it can be slow. Yes, yes. And yes, please.
Another question, I've seen like Filippo already in the class that there's also OP91 nodes now. Are those like also commercial RISC-V with the vector?
They are in the commercial, yes, what we call commercial RISC-V platform. They have, so I struggle a little bit call it vector unit because it's even less than the neon unit. So they support 2 elements on 1 vector, and as far as I know, they just support single precision.
Because I've seen that the CPU I think the V in the CPU.
Yeah. No, the CPU has a V, and they did the very early implementation. Strictly speaking, they are targeting video encoding or this kind of small embedded. But I actually would not suggest to start developing there because the Linux image is, I mean, is a typical say Chinese technology that has been shipped there right first. Everybody bought them, and they released 1 kernel and they never update. So you are basically that's why we do not advertise it. But yeah, I mean, this is recorded, right? Maybe I should be careful with my. Okay. So, and yeah, this is pretty much stable, I would say. So I would go here. Here, for example, you can even have different flavor of Ubuntu. We have 1 node with an Ubuntu that is older, other nodes with the newer Ubuntu, and we update it and so on.
Your changes to the LLVM compiler, are they public or how can I get them?
We have both the compiler and the behave available in binary form in our FTP right now, so you can have it anytime in binary form. And the plan is to have it pushed upstream at some point during the project. I mean, we are constantly in contact with the LLVM people, but as far as I know right now, what we are supporting here is not upstream. Not because it's not possible, it's just because it's a parallel development and it's not going back upstream, but you can have it. Everybody can have it. In principle, what I'm doing now on this machine, you can also do it on a QEMU image. Of course, it's slow, you know, but in principle, you can also do. So I can give you, well, you can build your own QEMU RISC-V image. We give you you download the compiler and the emulator, and you do it on your lab without the need of any RISC-V app. We go forward, otherwise. Anything else? Okay. So the example was, as I say, we are working on 3, say, loops or functions that are completely synthetic, so don't try to find some physical meaning on this. We have a data structure that is XYZ. It's called points, and you have a point with 3 coordinates, basically. And we have compute points that is doing some computation on the coordinates of these magic points. We have a permute that is just shuffling around data within directions. So this is the kind of things that probably you can have when you have sparse structures. And here you have the compute 3D, in which you have a mix of the things. You load from the memory, you do some computation, and you store. Okay, so these are the 3 loops that are in the code. Okay, so now I jump to so I have the slide support in case something fails, but what I would like to do now is jump to the shell, so I sit down and I show you. So I already loaded the modules. I am sorry, this is my home, so I go to the Plasma-PEPSC tutorial. Here I have my files, the make file. If I do the SRC Scala version, of the code, you will see the four functions that I've shown before. So compute point, you see my pointer. Okay, so compute point, compute 3D, and permute, and the main function that is called it in a loop. Okay, so nothing. So what I've shown in the slide is in the source code here. So if I do make Scala, I have my binary here and dot slash this binary, and I get the number of cycles that I need to execute it. And right now I compile here and I run it here. Okay, so nothing, but so yes, please.
At what point did you jump to from the gateway or logging out to the platform? I didn't see that. Or you land directly in one of those?
No, sorry. So if you didn't see, so the green shell is my laptop. Now I jump to say the login node of our lab, and then I do SSH RISC-V.
So every time you clear the screen, we don't see what you type because it goes on the top and there's a line there. So
I try.
that's why they miss that line. So just that, not clear the screen. So.
Yeah, but I mean, well, I prefer it, but okay. So if I do like this, you see?
Yeah.
Okay. So SSH RISC-V. And this is, so you see the name, we call this cluster arriesgado, for obvious reasons. So you end up in arriesgado 11, that is one of the nodes that we use. Okay. So I reload the modules now because I lost my environment logging out, right? And I go back to my folder, and in the bin folder I have my Scala code. Now, what I did with just two commands now, make Scala and executing the Scala code. Here for your code, it could be a week of work, right? Because if you have some code that some part of the code that is not supported in the compiler, if you have intrinsics or if you have dependencies with external libraries, I mean, right now I'm compiling 3 loops, everything is embedded easy, right? But it can be tricky. Okay? But we saw so far that you always end up in having some decent configuration in which you can run. Yes, please.
And if they are missing some library, they can ask for that. So some of them will be available, like MKL, but I don't know, the last thing we installed is RISC-V.
Yeah, I while you were saying this, I said I did module away, and this is say what Marco was showing yesterday in that software stack is basically what we have here. Right now is say a small list. We can grow this whenever you ask for some item.
So tool chain is based on Spark or what?
No,
Easy build or nothing?
the tool chain right now is based on us compiling from source code and deploying the modules. That's the current situation.
Modules by row.
Yes. It is done like that because it's still a small setup, right? So it's still, we still can control it and it does not diverge. And as I said, we have all the same, is the same Linux kernel and the same Linux distribution that is running here and here. So in principle, the same binary that you generate here, not in principle, the same binary that you generate here runs here. So we have a shared folder that is called /app that is shared through the network file system, and everything that is there is readable and executable from the computers. But it's important what Marta was saying. This list is incomplete today, but whenever you ask for something, we have one of the guys in my team that is dedicated to this to grow this list. Okay. When it was okay, so now I want to show quickly. Let's do this way so you see Yeah, so we did the make scala, right? So simply using the C flags that you see here, so nothing fancy. But now we do the vectorization, the vectorized version of this code. So let's see which flag. So you see here you have a list of magic flags that you should add if you want to try to auto-vectorize your code. But the important ones are this -m and LLVM and the MCPU Avispado. Right? These are the Avispado is the name of the core that we are using. So yeah.
-AP, no? The first one.
Yes, the -M-AP, yes, sorry. I say the -M and yes, the -M-AP is the, yes, please.
Is there some documentation about the flex in
Yes.
the message of the day, or where I can find it?
No, we have a wiki in which we have all the intrinsics, but not, so if you need intrinsics and the flex, I think. I mean, some of them are standard LVM, some are dedicated for this, but yeah, there is some documentation. Okay, cool.
What would happen if the other flags were there?
These are flags that we carry on. I would like to avoid it, but in principle, I would say that I could remove them for the sake of this tutorial. Never.
So if we have this access, we can try them.
Yeah, but we can we can pass to you the minimum set that you can try, and then optional ones that you can apply. Okay. This. Okay, so be aware that now I will compile with the auto vectorization. So it's the same source code that we get out. Make auto vectorize. Okay, and here we have the message of the compiler. So the source code is autovec.c. So if I do is basically the same as before. We have compute points. We just replicated for say the teaching reasons. So if I look at the messages that are related to autovec.c are this one, right? So we have message about the cross model, not really relevant, but we have then, this is important, right? Vectorized loop. So first loop seems that the compiler was able to auto-vectorize it, the second one as well. And the third one says, I don't do there, okay? So here, there is, if we go to see the code, there is a level of indirection that the compiler assumes that is unsafe to vectorize. Okay, so here we can put the pragma now to say this is safe to vectorize because we know that all the pointer are and well. So I have the code that is already. It has already the pragmas. So I'm putting the pragma of C-lang loop vectorize, assume safety, and we are happy. And now I will show you make that. It's doing exactly the same as before. We have the messages about back, and we have vectorized loop, vectorized loop, vectorized loop. Good. Okay, so yes, please.
What happens if you put this pragma on a loop that the compiler actually does not understand sufficiently enough to vectorize? Is there an error then, or
no? Not if these pragmas are. So you are telling a hint. If so, the compiler will try. If it's not able to do it, you get the Scala version.
Is there also an option to have actually an error? Because I imagine if I want performance and I also want guarantee that I get the performance. So if I put the pragma there, then maybe I want the compiler to say, no, I don't understand this, please remove pragma.
No, but I think so. If the compiler doesn't understand the pragma, it will ignore it, and you won't get an error. If you put the pragma, it will do whatever you tell him in the pragma.
No, what I mean is if I put the correct pragma, but if the compiler does not understand the loop sufficiently enough to vectorize it.
It will give you a friendly error message that it can't vectorize because, depending on why you don't understand it. With these flags, and at least gives you quite verbose information about why it does or does not.
Isn't the case that the pragma override is checked? So if it's open MP still P, it's like this, so you can vectorize the compiler do it, and in the worst case, you can wrong results.
Yeah, I think it's that. So if you tell the compiler to do it, we do it.
And
If it's
I don't know about this line pragma for open P.
So you want something like that working together,
Essentially.
or removing.
The question is this pragma a hint for the compiler, or is it you have to do it, and I hear about the object?
We have to ask Jay. I don't know.
Yeah, just have the question and say the answers.
Yeah.
Supposed to, is it mandatory to put the program, like it's needed or not?
No, well, needed or not is, so it's needed, but I understand what you mean. I mean, what are we, with a pragma, what are we telling to the compiler? That he needs to try, and if he's not able, he will do the scalar version and that's it, or he will do what we state in the pragma, and if he's not able, we get an error. I have no answer. We can ask, you're asking, okay. Say as a workaround your question, or well, workaround, I don't know, but what I'm going to show now is a method that is independent from the compiler to inspect where are the vector instructions, which kind of vector instruction are there, and also which is the vector length that you get. So, of course, we rely, so as an entry point, we rely on the compiler messages, but we have other methods to arrive where you want to be. Just one more comment, these pragmas are also useful if you have a huge code and you say, okay, let's do auto-vectorize. You could get easily a mess, right? You don't want to start auto-vectorize your, I don't know, initialization phase. So you can use the pragma to start working on just one small part of your code and tell the compiler, don't vectorize all the rest, just work on these 3 functions or these files, and you get the auto-vectorization just in that section. Yes, please.
Could I also use OpenPCD in this case, or is it not understood?
I think that is the case. No, okay. Here we use the pragma, but I think it's equally supported. Yes. Yes. Okay. So now I did make that, right? Make that. Did I do it? Yes, because we saw the message. Okay. So if I do /bin back, what will happen? See, so I'm doing the nasty picture now. What will happen if I do? I am on a scalar platform. I have a binary that has a scalar and vector instruction because I enabled the auto-vectorization. So I should get an illegal instruction, right? Indeed, I get. So unless I put our and this goes in the direction of the question of Leon yesterday. If I buy my own unmatched board, do I have everything I need? Not really, because the unmatched board doesn't have the vector support, so all the vector work, so basically would not work unless you put the emulation on top of it. Okay, so let me show. Okay, here, in case my network would fail, I was showing you the messages of the loop. Yeah, just a brief recap of how, can you see this image? Is it too small? Just how it works. So basically you have your Scala code that is running on a Scala CPU natively. At some point you have the vector instruction. So you have a legal instruction signal, you trap it, you emulate it in software, and then you go back to the native executions. And this has two effects. The first one, your execution of the vectorized code is very slow. The second one is we have this code that has if I run Scala, we report the cycles, right? So starting from now, when I emulate something, you will have a huge amount of cycles because you spend a lot of cycles emulating. So this will not be a measurement of your performance. So if you measure cycles, don't trust that measurement, right? Because you are measuring emulation time. Okay. So how do I enable behave? Well, in principle, I could do the I do enable in the make file as I showed you before, and this is simply command line to launch the job to the queue in order to run my vector binary with behave. Okay? But if I do, this has been done just to be faster, but if I do this, it's simply something that is taking the partition and passing the binary. Sorry. If I do in run behave, the run behave script is simply something that is setting up the variables that are needed. For example, this is an emulator. We want to emulate with our vector length. Our vector length is 256 elements of 64 bits each. So this is the vector length we want. We declare the vector trace file because when we execute with behave, we obtain also trace. So this is just, I just wanted to hide all this to you and we have it in a script, you know. And in the end, the command is always behave plus the binary that you want to run. So let me. So now the job is submitted, and if I use Q, F Mantovani, that is me, is running on one of the red boards that were, so the Scala ones, right? And this should take about 1 minute. Not because the emulation is so slow, but here we have two steps. The emulation is slow, but also we are generating a huge trace because every time that we execute a vector instruction, we trap it and we also record all the parameters. So if we start having loads scattered, load and store, we record all the addresses and so on. So we are generating a huge file with that then we convert to a trace that we can visualize. I think it's about 1 minute the execution. And then I have here, I will copy here. Yeah, the meantime I can show you. So since I launched a job, I have here the output of Slurp that says, you see here, I have an overflow of cycles in. And
Could you have a measurement of the emulated cycles? So that's not the one which I really run, but what would be run if I would have a vector processor?
No, in this setup, we don't have it.
But this would be the relevant comparison to Scala code. So you have less instructions or less cycles because you can do this many computations per cycle.
Yeah, but this is what we were saying yesterday. So in this platform, we cannot measure performance or timing, and cycles is quite different to timing. So in this platform, we just see the kind of instructions and the number of instructions that we are seeing. There's no relevant information about
Yeah,
performance.
I agree, you cannot measure times, but principally you could count cycles in the emulator.
It doesn't make sense anyway, because imagine that your code, it's just has a bottleneck with memory and it takes you a lot of cycles, and we are not taking that into account.
Say that it's not completely true, that it does not make sense. You could apply on top of this, say a timing model, such that every time that you have an arithmetic instruction, you apply some latency to your instruction. So then you can analyze an overall time, right? So basically, you do a modeling. But say we didn't do. In reality, we do have something like this, but since now we have the hardware in which we can measure it, so we are not going there because there is so much variability, as Marco was saying. You have access to the memory, some bottleneck and so on. So better to use this platform to just sanity check. Whenever you have a binary vector instruction, you jump to the real hardware. And there I can show you now that you do not only count instruction, but you can also count cycles. Let me see. Okay, so since I'm using the graphical interface for showing you the trace, now I'm syncing the trace from Barcelona to my laptop, so I can show you. Where is the PLD one? Okay, so the trace is, sorry, the time stamps is 9:45, so this is our run, and the trace is this one. Okay, so I open it with Parallel. So whenever you open it, you see that your trace is here, and I can open load configuration. I have behave configuration, in which, for example, I can show you the code phases. We call code phases basically the three loops, right? So, and you see color coded, blue is the first phase, white is the second phase. When I hover the mouse, you see the value.
It's quite small. You can see the bar, but not the text.
Not the text.
That's difficult.
No worries. What I'm saying is that when I hover over the color, you see. Is it changing? Yes, but you want to basically is where you are in the code. Okay. Now it's clear. So what we are seeing here is on the x-axis you have. Let me show this. Vector instructions. So here you don't need. On the x-axis, you have the sequence of vector instruction that has been issued in your code, and they are color coded. So if I start zooming in, you will see that there is an iterative structure. Every color means one type of instruction. Maybe you cannot see it, but the light blue here is DLE, that is a unit load, so continuous. And then we have an fmul, vector fmul, a fuse multiply add. So I don't know if you see, but basically I'm reading what is here. So anyhow, what I wanted to show is that you have this. So if you zoom in, you can see each of the vector instruction that has been executed. So on the x-axis, you have how many vector instructions being issued, and then you can just classify them and have them grouped in a table for each phase. You can see, for phase, in phase 1, you have vector add, vector subtraction, load, and store. Yes, please.
Is it a tool you wrote to steer into the data, or is it some handmade tool, or?
No, this is the same tool that we use to analyze. It's called Parallel, and it is the same tools that we use to analyze parallel codes on a cluster.
Okay, because is it possible to transform the this plot on the bottom into text that is searchable? Because this mouse wheel has one problem. If your program is long, you are searching something, and then you like to see what is the next command.
So our approach is the opposite. We are taking the text and converting it to the format of this navigator, because we are used to this. But we so if I do, so the answer is probably easier to show you. You see, you have this backtrace. That is sorry. Right, this is exactly what you want. Here you have your instruction, and here you have the decoding the instruction, and you have the register, source, destination, the addresses.
Okay, then okay, this is some text.
And this is a CSV that you can process without any problem. Yes. For our say, since we are used to this tool, what we do is we visualize it with this. Okay, let me go back because I have 5 minutes. So code phase we saw it, vector instruction we saw it, and the vector in histogram we also see it. So value, when I change value, I basically see the statistics of which kind of instruction are used in each of the phases: the blue, the white, and the red one. Okay. So one thing that we see here is that the white phase, it seems pretty long, but we don't know if it's okay or not. So how do we know if the vector instruction that we put here are, say, good or bad? If we are to take advantage of our vector architecture, we can look at the vector length. Okay, so if I go to, let me zoom just in the relevant part in which we know, okay, I copy and paste the time so that you see the same thing. So these are the phase, value 1, blue, white, and red. And here you have the vector length in a color code where green is low, say low values, and blue is high values. It's a gradient of colors. Of course, we don't have a gradient because we have just 3 phases, right? And so what we see here is that in the blue phase, we have a blue color. So we have 256 as a value. That is the vector length value. So that means that we are taking advantage of the 256 element in the vector. And this is good. Okay, so the auto vectorizer puts vector instruction, and that vector instruction has been fully used. We still don't know if that vector instruction makes sense, right? But we know that at least we are using the full vector. And this is true also for the red part that is more here, 256. And here in between, we have a lot of space in which we have a vector length of 24. So on a vector of 256 elements, you are using just 24. Okay, so basically we are wasting 90% of the resources of our vector.
What, 24?
24 elements of double precision elements. We used say the The unit is double precision element. Okay, so in Intel AVX 512, one register can house 8 double elements. AVX 512 is 8 double elements. Here we have 256, so it's way bigger. And what we would like to have is a code in which we take fully use of the vector. Yes, please.
What is the negative? The negative if I use only part of this long vector. So, but if it is still a multiple of 8, you said me that it is processed in blocks of 8 or something like that. Is it then the case that the vector pipeline is not filled properly, that you can then go to the next instruction, and that you have a gap there, you do nothing, or what is that?
I have an answer to this. That is, we use a matrix that is the vector CPI. Let me see if I have it. Load configuration. Vector instruction. Oh. No, I don't have it because this is emulated. So whenever I run it natively, I can show you the clock per instruction. So I will have a quantitative answer to your question in something like 5 minutes.
Yeah.
Okay. So, but yes, you are right. If I'm using a shorter part of my vector, is inefficient the use of the vector length, but I'm also slightly faster because I'm not going through the whole vector, right? I'm just using the first part and jumping to the next instruction.
But slightly faster means the next command is not ready at the point.
It could be that, but you also have to think that you have some overhead for, say, starting the vector instruction. So you are paying that overhead, and if you pay that overhead and then you compute on 256, that overhead became negligible. But if you pay that overhead and you just compute on 24, then that overhead, you are paying it a lot of time. So that's why we focus on that cases, say, okay, if we can take full advantage of the vector, is better. But still, there are cases in which, for example, you cannot use the full vector, but still you have some benefit. It's not used to say. Good. So what I showed so far is what you can do in the. Sorry, I go back one moment to the slides. What you can do, you are free to do in the Scala platform. Okay. Now, yes, please.
So how can I find out the reason for this 24? The next 24 can I also. So principally, I could try to optimize this and get longer vector lengths by rearranging the code or whatever.
The reason is actually in so is what I'm going to show now. So basically, we are in the phase 2 of the code that are 2 nested loops. And if I go to the error, sorry, in the warning message or the messages of the compiler is telling, hey, in this phase you have 2 loops. I'm vectorizing only the innermost, because that's the behavior of most of the vectorizing. Okay? So what we did here, I'm not saying that you have to do it in your code, so please don't get me wrong. And what we did here, we fused the 2 loops so that the vectorizer is probably able to vectorize it. So if you don't have nested loop, the vectorizer can work on the hierarchy of loop that you have, so you get the vectorization.
Is there another possibility instead of changing the code?
We are working, I know that Roger is working on having, in some special cases, auto-vectorization working also on nested loops, for example. But I would say that starting from here, you are in a situation in which actually that's the great situation of our consortium, that you know the code, we know what to do. So if we start this study together, we need to take the code and say, okay, we have this, we cannot take it back. For example, in another case similar to this, we did the swap of the loop, right? So you simply swap the loop, and the external one has a longer say it swipe a longer set of indexes, and then you get the vectorization. But it can also be that due to your data structure, if you swap the loop, you start putting some holes in the data. So the compiler start putting, instead of a contiguous load, some scatter load. So it's really something that we have to look in.
Ideally, the compiler, at least this loop fusing collecting should be done automatically by the compiler, the auto vectorizer.
Yes.
If not, then at least you can use some of the collapse clause, which is doing exactly this.
For
It's
example.
already there, you have to rewrite it.
For example.
The shuffling of the loops, I don't know, yeah, some compilers are doing it, some cases.
Yeah.
You have to do that, right?
Yes, please.
Did I get this right? That if in a loop, we call it if L was larger than 256, would we have been fine already with the first object?
True. Yes.
Okay.
Yes. So what we did was this fusion. So if I quickly go back to I'm basically now using, I'm telling the makefile to use not the vec.c, but the vecfuse.c that has this change in the source code. If you want, we can show you, but just in the interest of time. So now I can submit the maybe I can execute it directly in the FPGA.
Yeah.
No, let me just do this.
Why do you actually use batching there?
Sorry?
Why you actually use as batch if you have just
I'm using as batch because because this node in which am I now is a Django. So it could be that I have somebody else running there, somebody else compiling. So in the moment in which, for example, I'm looking to benchmark something, is not healthy. See, it's just for that reason. So, but anyhow, why this is going? What we will have now is a situation in which all this bar is blue, spoiling the end of this. Yes, please.
So now that you fix the loop, we should run faster.
The execution, the emulation.
The execution, yeah.
Yes, it will become faster because you have to emulate less vector instruction. And so it will be slightly faster. This has finished. So if I put this in background and I go back to the sync, okay, this is my I'm opening now the vecfuse trace. So now I have two traces open here, the vec instrumented and the vecfuse. In the vecfuse, I apply the same configuration as before, that is the vector length. And now I go back here, the vector length. It's this one. I copy the time, paste the time. And you see two things. First, you see that, sorry. First, you see that everything is blue, so you have 256 everywhere. So I'm using the full vector length. And the second thing that you see is that we use significantly less instructions, right? So on the x-axis, you have the number of instructions. The window have the same time frame, so you see that we are compact. It doesn't mean that your code will be faster, right? Because if I'm putting there instructions that are it takes requires a higher latency, that could be that it is not faster. Okay. One thing that I want wanted to show on this trace is the number of vector instruction per phase. Okay, so here you have below you have the vector instruction of the first execution without, say, the loop fusion, and on top you have the one of with the loop fusion. Now let me go to the value 2, that is the white part, value 2.
So we cannot read the numbers, but they are color coded. So blue means high, green. So you can just look at the colors. Green is low.
Now you can see the number, right? So yeah, basically what you see. Well, ignore the nanoseconds here, but all the this is the multiplication, load, store, and fuse, multiply, add. You see that all the numbers are basically scaled down, and there is almost a factor of 10 in the arithmetic part. That is what you expect, right? Because we are using a vector length that is almost 10 times higher, so you have 10 times less instruction, sort of. Right, because we were using a vector length of 24 in the case of not optimized. Now that we've used the loop, we have a 256 vector length, so we have almost a factor of 10, and you have almost a factor of 10 in this number.
But I don't understand.
So because you have identical windows, I can't tell which is the case which has been optimized. In this two windows,
The bottom one is the not optimized, the top one is the one.
Yes.
So the smaller is better in this case because you do less
instruction.
Less instruction. In reality, if I do like this, you see both. No. So what here you have the one that is not optimized, in which you do here. Here you do smaller vector length, and here you have all blue, so higher vector length, smaller number of instructions instead.
But I don't get this why you cannot say that the optimized one now is also fast. It's just to latency hiding of the memory bandwidth or memory loading, or why? In principle, I want to have a fast code, and I don't care if it's using 24 byte doubles or 256. I want to have the fastest code. And at the moment, I was thinking, okay, the longer the vector length, I can use it, the better. But you said that it's not clear.
No, in this, okay, I agree with you. In this case, we did such a trivial change on such a trivial code that we are 100% sure that will increase the performance a lot. But let's assume now that you do a code change that affects your data structure. That is that the compiler will see. We have to put a load that is not contiguous, but is a scatter load, a gather, sorry. Right. So you change your code in order to take advantage of the full vector length. That is in principle good, but you are removing contiguous load. That is the sort of coalescing that you do. So you don't load a chunk of memory, but you start to adding the overhead of computing the pointers, the addresses of all the data that you have to gather from your sparse, say, data structure.
Okay, so it's about the data loading, because the vector instruction, it's always better if I use the longer vector length. It's just about getting the data from whatever memory cache.
Yes. So in the arithmetic class of instruction, you always gain if you, yes. It's true. If I change, the only part is in the data shuffling. Shuffling, I mean, it can also be that you introduce some reduction or some movement of data within the bank of the registers. That's also something that can introduce some overhead.
So but in the end, I have to run a profiling on a real platform to see what is faster.
Yes.
I can't see it from the profile. So I can't see it from the length and usage of the vector tracing.
Exactly. In fact, what I wanted to try now is, you see, I can put the FPGA job now with the run instrumented FPGA script, and I send this job and the one without the back fuse, that is only back. Okay. Now I'm jumping faster to the FPGA. So now I abandon the emulator and I run natively. Okay, so run natively means that I can collect cycles with the PAPI counter. So it's the only difference that compared to something that you know is that it's slow. Okay? So it's 50 megahertz. But the rest is everything that you are used to. So we collect cycles, we can compute CPI, IPC. The problem here is that these will take 5 minutes. They will run in parallel because I'm taking two pickles, two different systems. But so yeah, this will take 5 minutes, and I'm already out of time. If you agree, I have the traces already downloaded in my laptop because I did it last night. So I jump directly to the traces. Okay. So let me see. I would tutorial, extract traces. You see, these are the two executions at 1:40 last night. I can show you the ERB parallel. I really wanted to show because here I have the answer to what René was asking. Let me close parallel so that we don't have. Now we don't have emulation anymore, right? So I'm loading the VEC without the loop fusion. And the VEC fuse. Okay, I have the two traces loaded now. If I load the configuration file, that is the one of extract. Why don't I do it? The one of extract. What should I see? For example, here I have total cycle per phase, vector cycle per phase, for example. So here I can see, but let me jump directly to the CPI so that we have the number that I want. So configuration, vector CPI per phase. Let's ignore, let's just look at this thing. One moment. I close this, I close this. This is the without the loop fusion, then I go here, I go to the previous configuration, vector CPI per phase, bam, bam. Okay. And now it's zooming. So let's try to understand this, and then we are happy. Okay. So what is this number? Is the vector CPI in each of the phases. Vector CPI means the number of clock cycles that I spent in vector instructions divided by clock per instruction divided by the instructions. Okay, so I have basically the latency, the average latency of each vector instruction in that phase, right? Because I'm basically dividing the number of the cycles divided by the number of instructions. So how more or less is the average of the how much cycles I spend for each of the instruction in that phase.
So lower is better.
Low, well, depends. Lower is better if you are running the same in the two configurations, right? So we know that we are interested in the compute 3D phase, right? That is the white one. The other one, we didn't change it, and indeed the number didn't change much, basically represent that. Okay. Here we know that this is the back fuse. So here we are using less vector length. Okay. So the vector CPI is lower because we have more instructions, and for each instruction we are processing less elements. We know that we are processing 24 elements instead of 256. So the vector CPI is low, but is not good, right? Which you need an information, which is the ideal value. Well, the ideal value for the arithmetic instruction, we can compute it. We have 256 elements, and we are processing it for the implementation that I'm telling you is processing the 256 element in 8 by 8 elements. So we need 32 cycles for processing an arithmetic instruction. So what we would like to have is here a number that is close to 32. I'm now ignoring the tails, because if you have something that is not multiple of 256, you have some tail to do so, right? So, and that's the reason, because it's not true that lower is better, but ideally here you would like something around 32. And indeed, it's what you have here, is 4. Okay. Here you need some architectural information to do this analysis, and that's why we need to do it together, because these numbers can mean a lot and can mean that we have an error, or that we have a suboptimal use of the architecture or not. Okay. Now I was focusing on just this phase. There is a longer tutorial that we did a full afternoon in Juli, in which we also go on with the other two phases. I'm not planning to do it. I'm just now sharing the data for you. So if you want to, yes, please.
Would it be better just to compare the total number of cycles for these two things to have some better comparisons without any architectural knowledge?
Thank you. In this case, yes. But this gives you a little bit more insight of which are the effects or the alternatives. But yeah, you are not right. I overkill this. I take the code phase. I assume.
I think it's also about looking at from a different angle. So from the angle of the application, you're more interested in the total number of cycles, because that tells you how fast you are. From the point of view of the code design, with the hardware, we are interested in that to understand. So I think it's a nice thing that with a single trace you have a lot of different angles to look at that, a lot of information.
So here is the answer to this. So this is the killing factor to what you were saying. So I have
So now be careful, because now in the x-axis you have time. So before it was not time, it was number of instructions. Now really shorter means shorter execution time.
Yeah, but this also means that since there are two different runs, I have slightly different alignment of the cycles. But the size of this window is the same time window here and here. So you see that the blue phase is, well, the overall time squeezed. And the overall time squeezed due to the squeeze of the white part. That's it. So we are going faster, we can go. But as Marta was saying, if we want to take the other angle, we can also understand why we are faster here, because we know that we were using a suboptimal vector length. The CPI, the vector CPI is this one. We expect a vector CPI of 32, right? Because, for example, it happened once that in the early days, we never got 32. And you say, so why we do have 37 instead of 32? And digging, we discovered that in the RTL, there was a suboptimal implementation of the FMA that was, instead of using 32 cycles, was using 3 more cycles. Now you say, oof, 3 cycles is nothing. But if you accumulate that inefficiency over all the vector instruction that you're doing, it's a lot. It's 10% basically. So these kind of tools allow us also to go back to the RTL guy and say, look, I expect 32 and I see 37 or 35. So why is that? And sometimes happen with this, say, early implementation that you find something that is a feedback for the RTL. That is not a bug. Functionally, that RTL was perfectly working. It's just something that allow us to tune. This is a stupid example, right? It's almost debugging. But there are other cases in which we can go back, like, for example, if I have this architecture allow us to have 3 loads in flight. Doing this kind of analysis, I can discover that if I have 4 loads in flight, I can have a better throughput in my application. So then we can ask ourselves, okay, is just my case, or is it true that having 4 loads in flight has beneficial effect on all codes? We can quickly test it and go back to the RTL team and say, look, just give me 4 loads in flight. And they say, oof, that's a lot of silicon more, you have to pay more. No, just give me for the FPGA. In 2 days, you have it in the FPGA because you have all the CI stuff. And you test it. And if it is true, your guess that having 4 loads in flight, that's something that you start discussing, okay, how much silicon does it cost this? Does it make sense to have 4 loads in flight? Which other side effect do we have? And that's the kind of co-design that we are able to do because this architecture is sort of an early stage. Right? So some things are bad debugging for the compiler or for the RTL, but other things are really to improve the efficiency of the machine.
So the silicon design is not yet fixed. This can be changed.
Yes.
It's modified.
Yes.
About this graph, we go ahead. These 3 phases are always fixed to one pragma instruction.
In this case, yes.
What do we example when we have more phases? What does this phase mean?
Phase means is something that I didn't show. Is basically where you instrument your code. You can put, say, an instrumentation. Instrumentation code that allow you to say, okay, I want that these 10 loops is my solver. I don't know what, right? So, and you know that every time that you see blue, that will be your solver. But it's something that you can do on your code.
But you have 1 for loop and you have 3 colors.
We have 3 for loops and 3 colors.
But you're showing only one for loop at a time. But you're running all of them.
I'm running all of them.
So
I'm changing only one of them, but I'm running all of them.
I see. So each color actually is 1 for loop.
Yes.
And 1 change to 1. Because I thought you would change. I thought you run only that loop, and then you modify that loop, but we see only a short, so not an extreme change, but something, only a small change. So I thought, how come you change the whole loop? But at the end, you have a small change. Because actually, you're also running the other loops.
Yes. So whenever I run the full execution of the 3 loops. But I'm touching only one, the white one. So that's the reason, because you see the overall execution that is shrinking. But so this is the same size of this, and this is the same size of this. This is shrinking. And basically I'm looping and I'm doing. Okay. I jump to the last slide because in the last slide I have a bit of data for all of you and I want to share. So, well, all of this can be in Basecamp. I think all of us have access, or almost all of us, but anyhow. So, this QR code is pointing to a wiki page that is the first link, in which we have all the tutorial that I mentioned, all the material of the tutorial that I mentioned. Okay? It's not exactly what I've shown, but the code and the 3 loops and so on is something that you can dig in and see what's there. Then, the second QR code is the link for the form for having an account. So if you want to start playing, let me stay this, so he's already scanning it. So ask for an account, put Plasma-PEPSC as the project, and Filippo Mantovani or Marta Garcia as the responsible in BSC. And within a couple of days, you will have access. It's not the BSC infrastructure, it's a research infrastructure. So it's not handled by the same people of Mare Nostrum. That means that it's linear, it's simply just our lab, so we don't have to go through a lot of bureaucracy. This also means that failure are higher than the operation works way better than us. But anyhow, sorry?
Be nice.
Be nice. These are the three links. Yeah, SDB tutorial, that's the tutorial that we did in UV. There is more or less the same material. There is me talking 1 hour about RISC-V, but there is not what you have experienced now, because the tutorial part has not been recorded. But there is a video of me explaining all EPI. Then we have these two papers are one about the inefficient implementation of the SPMV, spasmatic vector algorithm for long vectors. And the second one is an efficient implementation of FFT. Please, especially Tilman that was mentioning yesterday, the NEC Aurora. So in both of these paper, we are using the NEC Aurora as a platform for testing our implementation. And then we have these two other papers. So this is software development vehicle to enable blah, blah, blah. This is basically explaining the methodology of what Marta was explaining yesterday. So you start working on compiling the Scala code, see that the toolchain is okay, then you jump to the behave and you start seeing the instruction, how well is vectorize your code with the vector and so on, and then you jump to the FFT. And this is a more philosophical reasoning of why so long vector is good in HPC, also in workload that are not dense. Well, for dense workload is trivial to understand that it's beneficial, but for non-dense is not so trivial. So there we do a little bit of study. It's not for doing advertisement, it's just to give you more material, because sometimes during these days I have the feeling that people are saying, oh, you're just saying this and you don't give us an account, you don't give us material. So take the account, take the material, play and break it, and we will fix it. And if it's in a too early stage, just be patient. We will have a test sheet soon with 2 cores, probably. We will have another FPGA implementation next year, so things are rolling. Half an hour delay, just like this.
Okay, maybe some discussion. And like coffee break or something. Questions? Like,
It's like being in a concert. Feeling bombs. Yeah,
so Planck is quite popular compiler for AMD such architectures like allows you to have these plugins for implementation. But
yes,
so does GCC. Is there any play with this more common compiler?
more common compiler. You mean you are asking about the support that we have for GCC for this kind of infrastructure, right? As I mentioned yesterday, you can ask us to have the GCC infrastructure there, the latest. There is I know that there is some support in GCC for the vector instructions. It's not optimized for this architecture. What does it mean? It means that, for example, we know that we can load something from the memory that is a huge load instruction that takes a lot of cycles, and in the meantime we can overlap arithmetic vector instruction. So this is a scheduling thing that is inside our compiler that is proper of our architecture. So that kind of things you won't have it in GCC, right? Because that's the kind of optimization that is, for example, related to the scheduling that is not there. But if you take GCC today and you compile, you probably will get some vectorization there that is meaningful and should work. We just do not promote it because with our compiler, we know that we can fine-tune a more efficient use of the vector unit. But you can use the GCC compiler.
So I thought that this overlap of instructions is actually a processor feature, like Intel and AMD to execute 4 instructions per cycle.
No, but what I'm...
What would the vector, can you do some more with processor or not, like store load be done?
There are features that are architecturally, that are architectural features, but there are features that are in the scheduling of the compiler. For example, if you have to do 4 loads and 4 arithmetic operations, you can do load, arithmetic, or you can do it this way. That's the kind of things that the compiler is deciding at compile time, how to put the instruction there. And what I'm saying is that in our case, we know that sometimes it's better to do this instead of doing this. But for example, if you have a lot of register, or if you are able to coalesce this, because you are in another architecture, the compiler knows about that and tries to maximize all the memory instruction first and then all the arithmetic instruction later. You know, that's an architectural thing. That when you put minus M CPU Skylake, you put it exactly for this, because there are hints for the compiler how to schedule the instruction optimized for that architecture. Did I give the idea of what? So there are things that are architectural and things that are really in the compiler, in the scheduling policy.
Yeah, so you showed like this loop fuse to help the compiler understand the nature, but like there are other most common like unroll loops that would be used for a small, let's say, vector size. I guess that this is part of, let's say, this pragma development for such things to be effective. So what instruction you could use together with vectorize? Do you know? Or actually,
let me try
doing this plugin development for
our office mate. So, so let me put it this way. Right now, we have an infrastructure that is supporting the vectorization that I've shown. That is probably not enough, but allow us to work with some vectors. Okay. The good point of Plasma-PEPSC is that if we study one code and we see that you have this structure of loops that requires the nested loops support, we can detect that, go to the compiler guy and say, put this first in your list, Okay, because so right now we have, I mean, of course, the compiler guy has his watch, right? But we are in a stage, as Marta was saying yesterday, we are in a stage in which we can drive this. And we decided that we want to drive it with science, not with the benchmark. And Plasma is one of that science. So probably what you need for your code is not there, or not all you need is there. But we can give priority to what is needed for our codes, in case it's not there. First, we have to study. And I admit that we just started with Glaciator and a little bit with the Chin. That's what we. So we can start with another application and see where we get.
So I have seen in the past this Mont Blanc and all kind of, let's say, promises that were somehow to become something like European or but in your opinion, what will happen after 4 years?
Could you please? Thank you.
Can you please?
Yes.